check. Hopefully everything's working out. iPad seems good. Get rid of all the scribbles. Can you hear me well? Testing, testing. 1, 2, 3. Right. A little bit started main. Magnus, if we have any issues on the stream, I need you to come here and notify me immediately. Alright? Hopefully I'm able to catch any chats that pop up. So, anybody who's new here, if anybody comes in, please just send a chat. That way I know you exist. Otherwise I'm gonna completely ignore your existence. Alright. So I'm gonna start by reading this chapter. Already led the introduction, but pretty much. This is chapter 11. Dealing with a balanced three-phase circuit. Right? What does it mean to be balanced? What does it mean to be three phases? Okay? Right. So that's what we're trying to learn today. Alright, I kind of drew out for you guys here on my iPad what a three-phase circuit may look like. Yeah. No. Just. Alright. Well, let's ignore that for now. Maybe someday I can get something figured out. Wait to be able to hear it play. But, yeah. Let me go. Alright. So, transmission. Alright. Transmission. Distribution of electric power. This chapter mentions circuits that are designed to handle large blocks of electric power. These are the circuits used to transport electric power from generating plants to transport electric power from generating plants to both industrial and residential customers. All right? All right. So what does this mean? All right. So we're considering a power system here, which involves three things: a generator, a load, and wires that bring power from the generator to the load, right? And the load could be a business, it could be a bank, it could be an ATM, right? It could be your house, it could be a toaster oven, like anywhere I'm trying to get thing of power to, right? That's my load. Okay, so we're considering a system with these three things. All right. All that matters is we got a generator and a load, and we're trying to transmit power there. Okay. So, I introduced a very basic residential customer circuit in the design perspective for chapter 1. All right, guys. They're just saying that we've already been over this chapter 1. So, now we introduce the type of circuit that delivers electric power to an entire residential subdivision. Okay. Oh, well, they consider it like a power plant to a house, but now we're considering an entire system where I have a bunch of things connected. Very intricate manner. All right. So, one of the requirements imposed on electric utilities is to maintain the RMS voltage level of the customer's premises. What the hell is that? All right. RMS. That's what means square. Okay. It's a way of taking a sinusoidal voltage, right? Because we have AC voltage, and you can kind of do this circuit analysis of the behavior of the circuit by converting that AC wave somewhat into a DC behavior. Okay, so to do that, we take the average of all the power. All right. And the only unfortunate thing with averages is, think about a sinusoidal wave. First it's positive, then it's negative, positive, then negative, positive. Goes up and down, so far on into infinity. But the positive portion is exactly the same as the negative portion. So when I take the average of something, the way that we do this in mathematics is with an integral. And you know how integrals work. If I'm taking the integral of a function, all I'm really figuring out is the area under a curve. So if I were to take the average of a sinusoidal wave, everything's going to cancel out because the positive area under this curve is going to negate with the positive area, the negative area over here. And they're pretty much just going to negate each other off into infinity. So the average is always going to be 0. So to avoid this, we have to root in the square. What does root square do? Well, if I square something, it's always going to become positive, right? If I take the square root, it's going to give me back the answer. So, root means square. Or say square my sinusoidal function, so everything's positive. Then I get the average, because everything's now positive and nothing's going to cancel out. Then I can take the square root of that and undo the whole square that I did earlier. And it's going to leave me with the average value of the sinusoidal wave. Okay? Yeah. Back to the reading. So, again, I want to start again from a sentence I already started. One of the requirements imposed on electric utilities is to maintain the RMS voltage level at the customer's premises. Okay? So, maintain our average voltage. So, if we have a sinusoid, spot up and down, we don't want it fluctuating at a ridiculous amount. Even when there's other random loads being, derived from the power. All of a sudden I turn on my toaster and my oven. No, I don't want it to go out of whack. Even though they're all connected, they need to behave the way that they're supposed to. They need to maintain that constant voltage that they are requiring, right? I think in our American sockets, this may be something in the magnitude of about 240 volts, right? You need that 240 volts, it means square. Okay. So, when it lightly loaded as at 3 a.m. or heavily loaded as an afternoon or a hot humid day, the utility must supply the same RMS voltage. Same concept of what I literally just said. All right. No matter whether there's a heavy mode or the circuit isn't really under too much stress, right? It needs to have the same output. Okay, so that takes a little bit more thought and a little bit of work. To satisfy this requirement, utility systems place capacitors at strategic locations in the distribution network. The capacitors supply magnetizing bars close to the loads, requiring them adjusting the power factor of the load. I may illustrate this concept after we have analyzed three-phase circuits. Okay, so we're going to first learn about three-phase circuits, and then we're going to try to understand how the systems of different three-phase circuits are able to utilize these capacitors to kind of maintain this balance. All right, we're all familiar with this, right? You've seen this before. You live in a Mac, right? So back to the image of the system. All right, we're going to start this little figure. Okay, you start off with a three-phase voltage source. These lines represent each phase, right? Each one is distributing power, and every single current in these lines are all, you know, they're based off of these three-phase voltages, okay? Then the load also must be three-phase, because if my source is three-phase, if I want to get all that power, I'm going to have a three-phase load. So either a Y or a delta, okay? All right. 11.1. Balanced command phase voltages. So right now, this is where the chapter actually begins. Everything before was just a stupid introduction, so I wasn't really explaining much. But here, I'm going to get into the nitty-gritty of details, okay? So, first paragraph. My ideas are going to read a paragraph, and then explain the paragraph after I read it. A set of balanced three-phase voltages consists of three sinusoidal voltages that have identical amplitudes and frequencies, but are out of phase with each other by exactly 120 degrees. We refer to these three phases as A, B, and C, and use the A phase as the reference phase. Three voltages are referred to as the A phase voltage, the B phase voltage, and the C phase voltage. Alright, recapping this paragraph. So, we got three voltage sources. They're all connected, and they're all in phase with each other. They're sinusoidal voltages, meaning that they're going to have sinusoidal waves representing their voltage, right? So there's going to be a maximum voltage at some point. There's going to be a minimum voltage at some point. What this is saying is that for them to all be in phase, they need to have that same maximum and minimum. The only difference is that they're going to be shifted out of phase. Now, if you're familiar with sine waves, you know that I could add and subtract to the angle that's within the argument of the function for the sine wave. And what this is going to do is it's going to shift it either left or right. Okay? So, at some point, although these two may be the same waves, if I shift them, it's going to look a little bit more like their peaks are at different points in time. Okay? So if I shift them exactly 120 degrees apart from each other, and need A to be the reference phase, A will be said to be 0 degrees out of phase, B could be either positive or negative 1 out of 20, and C would be the opposite of B. So if bin is maybe 120 degrees out of phase, C would have to be positive 120 degrees out of phase. That way they're all 120 degrees out of phase from each other. Okay? So, continuing the reading. When we two possible phase relationships can exist between A phase voltage and B and C phase voltages. One possibility is for the B phase voltage to lag the A phase voltage by 120, so minus 20 degrees. In which case the C phase voltage must lead the A phase voltage by 120. So if B is negative, C must be positive. B is negative 120 degrees, and C is positive 120 degrees. Okay? This phase relationship is known as the ABC, or positive phase sequence. In phasor notation, you see that the ABC phase sequence is this. Okay. So, let's try to learn this very important phasor notation. We got these three voltages. Notice that these are bold face, okay? They're bold because they're vectors. Alright, books, instead of writing a little vector line, they're in this. So they have a magnitude and a direction, right? The vector is a magnitude and a direction. All we need to write down for polar coordinates is the magnitude and the direction. That's what we use of M stands for. It's the magnitude of the voltage, well, the maximum of the voltage. So the maximum voltage is the magnitude, and this angle right here is the direction. Alright? Now, you're probably wondering, how does this represent a sinusoidal wave? Okay? It's a little bit complicated, but if you're familiar with point wonders and imaginary numbers, this stuff makes sense. So just try to think about it as if I have this wave, the very top, the maximum, is the magnitude, right? And this is the phase shift, so the amount that the wave has moved left and right. Okay? Don't worry about the rest of the nitty-gritty details for now. Just try to understand that a positive phase sequence, an ABC sequence, is 0, negative 120, positive 120. And a good way to remember that is a negative comes first with a positive sequence. And obviously vice versa is going to be for the negative sequence. For the negative sequence, we're going to have a positive 120 and negative 120. So the only other possibility is for the mid phase voltage to lead the A phase voltage by 120 degrees. In which case, the C phase voltage must lag the A phase voltage by 120 degrees. This phase relationship is known as the ECB, or negative phase sequence. In phase notation, the ECB's phase sequence is what I just said earlier, right? Instead of negative 120, positive 120, we have positive 120, negative 120. You may be scratching your head and saying, why do scientists always do this? Why? Gonna have to make things more complicated. Why not call the positive phase sequence the one with the positive number first, and the negative phase sequence with the negative number first? To be able to fully understand this, you are going to need to be able to visualize the circuit. Okay? So I'm going to pull up here the visualization. I'm going to use over this troubleshooting, setting up something nice for you guys, okay? Alright, so here we go. Alright, so now everything's out of the way and perfectly exactly how I want it to be. Okay? So, let's start from the beginning. Well, what exactly am I going to do right now? Alright, I'm going to show you guys a circuit simulator that allows you to visualize what exactly I'm talking about. Right? We're going to go here to input sources, and we're dealing with AC voltages, right? And they're all connected in a watt, okay? Okay, so we understand that much. We've got 3 voltage sources. They all have the same maximum voltage of 5 volts. But this one, if this is voltage B, it needs to be negative 120 degrees out of phase. If this one is A, we're trying to show why the positive phase sequence is 0, negative 120, positive 1. Okay. So, we have 0. This one's positive 120. This one's negative 120. Okay. So, let's increase the speed here. See if you realize what's going on. If you follow this with your eyes, red, you'll notice that the red line is kind of rotating in a clockwise motion. That's why this is a positive phase sequence. And I don't know why it randomly stops. But it decides to randomly stop after a while. I think it's because it's not connected to anything. So let's try actually connect it to an imaginary load. here. And unfortunate. It doesn't like our theoretical application. You always have to put some resistors, right? So for now, so that things don't get too complicated, I'm only going to consider the resistance of the lines. You know what that means later. Alright, so let's connect these resistors. The generator. Whoa. Generator. To load. Right. No. That's a little bit more interesting. Yeah, I'm not entirely certain why it periodically decides to stop the simulation. But that is not no feature that I've seen before. Here, simple lag. Here it's running normally. Okay. All these three sinusoidal voltage sources have the same maximum voltage. Their waves, their maximum is 5 volts. If I were to make it a positive phase sequence where this is 0, this is negative 120, then positive 120, hold the red line. It's at the top, that's at the right, that's at the left, the top, and the right, and the left. So it kind of low point circulates in a clockwise manner. And that's my reason why we call this a positive phase. Right? Negative would be the opposite. He did it in counterclockwise. That's what makes that negative. Figure well, 11.2 shows the phasor diagrams of the voltages in equations 11.1 and 11.2. The phase sequence is the clockwise order of the subscripts around the diagram. Starting from VA, you can use the phasor diagrams to show that the sum of the three phasor voltages in a balanced set is 0. This important characteristic can also be derived from equation 11.1 or 11.2 to give this. Alright. Important characteristic. Adding up all these three voltages, VA, VB, and VC, which result at a point at an instant in time, total voltage is always 0. And that is part of the reason why at the center, if I were to draw a line, a wire, we hit it there, there's 0 current running through it, see? 0 current. No voltage, no current. Man, this thing is being really dumb. Try, opening a new instance of it. Hopefully I could just copy paste this. It just seems crap. Yeah, it does. My only assumption is that it has something to do with me streaming. So, that's unfortunate. This is a very big portion of what I wanted to show you guys, this program. So, I'm about to just end the stream right here.